Hey everybody, I'm Gilad. I'm going to be presenting a work with Itai Abraham, Philip Jovanovic, Mary Mahler, Sarah Michael John, myself, and Alin Tomescu about DKG. So, in very high level, our work has like 4 major protocols. The first one is a distributed key generation protocol. We have a consensus protocol, a proposal election protocol, and a gather protocol. Each one kind of feeds into the next one, and we're going to talk only about the first 3, the DKG, the consensus, and the proposal election. And we're not going to talk at all about the gather. It's a cool protocol. Come ask me about my protocols if you want later. So distributed key generation, what is it? What is it good for? When we work in cryptographic settings with cryptographic protocols, we generally assume a public key infrastructure. So each party can have a public key and a secret key associated with it, and parties can, for example, sign messages or encrypt messages. However, often that is not enough. In what sense isn't it enough? We might want a kind of more structured randomness. For example, we might want to have threshold signatures, which are a more powerful primitive. I'm going to talk about them a little bit more in the next slide. And that's a very useful primitive for consensus, for blockchain protocols, and we want to be able to do that as well, and the PKI simply isn't enough. So one way we can get that is we can have a central authority, some server that's going to sample some values and send each party their value. And that's good if we have that central authority and if we trust it, but we might not have that central authority, or we might not trust it. In that case, we need to have some protocol to generate that structured randomness. So in this case, we have a distributed key generation protocol, and that's kind of our goal. So here's kind of a schematic for a DKG, a distributed key generation protocol, specifically for threshold signatures. So in a DKG, the black box DKG protocol samples a public key, a secret key or a signing key for each party, and a verification key. And then it just sends each party the public key, their specific signing key, and the verification keys for everybody. And when we talk about threshold signatures, usually what we want to be able to do is each party wants to be able to sign a message. And then we also want to be able to take many such signatures. For example, usually we think of at least one non-faulty signature. So if F is the number of faulty parties, we want at least F plus 1 signatures, and we want to be able to kind of condense them into a single short signature that we can verify. And the signature is supposed to signify that we have many kind of individual signatures inside of it. And if we kind of think of a PKI, just the general setting isn't enough. We need some structure. We need a relation between PK and the SKs and the VKs, and we need to be able to generate that in some way. So our main result of the paper is that there exists an asynchronous distributed key generation protocol resilient to fewer than n over 3 Byzantine parties. The protocol requires a constant number of rounds in expectation and a quasi-cubic number of words, in this case specifically n cubed log n, number of words in expectation as well. And the state of the art requires at least omega of n rounds and omega of n to the 4th words to be sent. This is a work by Kokoris Kogias, Malki, and Spiegelman from CCS. So we're shaving off a factor of n in both cases. We use a few primitives from previous works. So the first primitive is a DKG shared generation. That's how we call it. This is essentially a scrape PVSS. Scrape is a work by Cascudo and David. So each party can generate a share. That's a small part of the DKG. And then we want to be able to take a bunch of these shares and aggregate them. So when we think of a DKG kind of process, we want to have input from at least one non-faulty party. Otherwise, the adversary might be able to completely set the key, for example, which is entirely insecure. So in that case, if we think of F being the number of faulty parties, then we have to have at least F plus 1 shares aggregated into one. And naively, this is very expensive. This can cost around n squared words overall, because each PVSS transcript is linear in size, linear in the number of parties. So we don't want to pay that kind of steep price. And the trick here is aggregation allows us to take n shares and aggregate them into a transcript that is still of size O of n. This is a work by the same group, this long acronym. It is very important that the transcript of the aggregated share includes, the aggregated DKG includes all the information we need. It includes the public key, all of the verification keys, and each party can also extract their signing key from the transcript. So how can we implement a DKG? So when I look at a DKG, the first thing I think is that the parties need to agree on an output. They need to agree on the transcript that they're going to use. And it's kind of agreeing on a non-trivial value is just consensus. It kind of has to be consensus. So when I look at this problem, the first thing I think of is consensus. Maybe I'm biased. I work on consensus. And if I kind of have this intuition, the natural solution, at least for me, is to do the following. First, we send DKG shares. Those are PVSS transcripts, which are of size of order n. Then each party aggregates at least f plus 1 shares. As we said before, we need at least 1 share from a non-faulty party. And then the transcript ends up being of size order n. We did these two parts. Each party now is supposed to have some transcript, and the next step is just agreeing on which one to choose. So the final step is reaching consensus on one DKG transcript. And if we look at this, the first two parts, or the first part is cheap. It requires n cubed number of words. The second one is local. And we need this third part to be cheap only using a PKI. We don't want to assume structured randomness to achieve structured randomness. That doesn't make sense. So for those of you that don't remember exactly what we mean by consensus, a consensus protocol, usually we think of it as having three properties. The first one is validity. If all parties are non-faulty and they have the same input, they output that value, x. The second one is correctness. All parties that complete the protocol output the same value. That's essentially the agreement part of consensus. And the final one, which isn't necessarily trivial in an asynchronous system, is termination. If everybody participates in the protocol, they eventually complete it. Now, this isn't actually enough for our purposes. So the keen-eyed here might have noticed that the two first properties are kind of the correctness and validity, allow for outputting weird values. If it is not the case that all parties have the same input, they can output anything, technically. And we want a DKG specifically. Like anything, we can't output the number 3. That doesn't work for us. So we have an additional property that's called external validity, and for our purposes, this means that we actually output a DKG transcript. That's enough for us. All right, so now here's another result of our paper. There exists an asynchronous consensus protocol resilient to fewer than n over 3 Byzantine parties. It has, in our protocol, we use order n-sized inputs, and they're all externally valid, as in they're actual transcripts. The protocol requires a constant number of rounds in expectation, and it requires quasi-cubic, the same complexity, n cubed log n, words in expectation. So if we kind of think of the previous slide, that the n cubed log n from here is the same n cubed log n from the DKG protocol. And the protocol only requires a PKI, which is important in our case. So kind of a general approach for randomized asynchronous Byzantine agreement. In '83, it's kind of like long forgotten history, maybe not forgotten, but history. Michael Benel showed a randomized asynchronous binary consensus protocol. Binary in the sense that we need to agree on the value 0 or 1. And this can be thought of as a protocol with a virtual leader. We'll talk in a second about the virtual leader. The key insight here is that the leader can be faulty, the virtual leader in this case, but can never be silent. If the parties need some value from the leader will always provide that value. The protocol proceeds in phases with a virtual leader in each one. And we kind of have this property that if the leader is non-faulty, then all parties participate pretty quick in a constant number of rounds. And if the virtual leader is faulty, the protocol still remains safe. So what does safe mean in this context? Safe means that if some party agreed on a value or output a value previously, let's say some value x, then no party will output a value x tag, a different x tag, in any subsequent view. So safe here means kind of maintaining agreement. We never output a weird value that is different than a previously agreed upon value. Now, those of you that are that know the hot stuff protocol or generally Paxos-like protocols can see that these two final properties are actually achieved by this type of protocol. So for example, in the hot stuff protocol, we know that if we have, we proceed in phases called views, and if a leader is non-faulty in a given view, we'll terminate fairly quickly, and otherwise we remain safe. And we're going to use hot stuff in our, the kind of hot stuff approach in our protocol as well. All right, so we know we have this virtual leader idea, and now we want to implement this virtual leader for our case. And Benel's original virtual leader was good for a binary agreement protocol, and we want to generalize it for a multi-valued protocol. That's kind of what we need here. Our generalization is a weak verifiable proposal election protocol, and it kind of schematically works as follows. In this type of protocol, each party inputs a value. We call it a proposal. And then the proposal election kind of black box or protocol chooses one of those values at random and then sends it to each one of the parties. Now we have kind of two weird words here, weak and verifiable. So what does each part here mean? The protocol is verifiable in the following sense. As you can see in the schematic there, the proposal election protocol also provides a proof pi I for each party. And the proof is a proof that the value was actually received from the protocol. So each party can actually send the value it received to other parties and say, here is the value I got, and here is a proof that this is the actual value I got. This is the verifiability part. The protocol is also weak in the sense that this doesn't always perfectly work. With only some constant probability, we actually choose a non-faulty party's input. And with some other probability, with a remaining probability, we do something. We always provide a value, but it might be a faulty party's value, it might be different values to different parties, but we always provide some value. All right, so here's another result. We implement or we construct a weak verifiable proposal election protocol. We use it on proposals of size O of n. And we construct such a protocol requiring a constant number of rounds and quasi-cubic number of words. This is kind of a theme here. As I said, this is a weak protocol, so our probability of success is 1/3. This uses the gather protocol. It extends the techniques of Canetti and Rabin, the Byzantine agreement protocol by Canetti and Rabin from, I think it's 94 or 93, and maybe earlier. And I'm not going to go into the gather protocol any further, but it uses similar techniques to kind of classics with adaptations needed for the verifiability. So let's talk a little bit about our consensus protocol. We call it no wait and hot stuff. It's an adaptation of the hot stuff protocol. It has two major differences from the hot stuff protocol. So those of you that know the hot stuff protocol can kind of imagine how it usually works. In the hot stuff protocol, we have a leader for each view. It can either be randomly selected or round robin kind of exchanging leaders. And unlike hot stuff, in our case, we have a virtual leader in each view. The virtual leader is implemented using the proposal election protocol, as we said. In the first round, each party inputs a proposal into a weak verifiable proposal election. And then, as we said before, the proposal election does one of two things. It either sends a single value provided by a non-faulty party to all of the parties. And we know that happens with a constant probability, in our case, a third. And with the remaining probability, no greater than 2/3 probability, it provides some value. It's weird because we don't know what value. It might be different values to each parties, but every party has some value and crucially also a proof that it actually received that value from the protocol. Then the next step is parties send their outputs from the proposal election to each other and provide the proof. And now we have a second kind of difference from the hot stuff protocol. In the hot stuff protocol, if we see weird messages, if the leader doesn't send anything, or if the leader sends a faulty message, we kind of wait until we reach a timeout, and then we move on to the next stage, the next view, sorry. And here we can't do that. If we're in an asynchronous system, we can't have timeouts. That just won't work. So unlike vanilla hot stuff, if we have an invalid message or equivocation, if we see two different values that are output from the proposal election, then we can actually send that to all the parties with proof. We can show them that these are actual values that were received from the PE protocol, the proposal election protocol, and that they're incorrect if they are incorrect. So a little bit of intuition, why should this protocol work? So we have two parts. The first part is safety. As we said, we don't want to agree on to output a wrong value, or a value different than a previously agreed upon value. And why should we have safety? So the main property of hot stuff is that if a non-faulty party committed to a value in a view V, then no other value receives enough support from non-faulty parties in any subsequent view or in V as well, V tag. So in any V tag greater than or equal to V. Now, by enough support, we mean enough support to kind of proceed into the late stages of the protocol. And we have this property as well. We use the same key and lock mechanism of hot stuff. And we kind of inherit this type of safety. Now, the only thing that might be a little different from hot stuff, the first thing I thought of when I looked at this kind of approach, is that we have a specific type of behavior that can't happen in hot stuff. And the specific type of behavior is having two different leaders, right? We can receive two values from different parties, and that's not a thing that can happen in hot stuff. But essentially, that's the same as an equivocating leader in regular hot stuff. That's the same as a Byzantine leader sending different values to different parties, and hot stuff knows how to handle that. We have safety in that case as well. So the intuition for liveness. First of all, the proposal election always provides values to parties. Parties never need to wait, but they're never stuck without a value. We never need to wait for timeouts. So we have kind of two parts of liveness. We want liveness in the case of a non-faulty leader, and we need liveness in case of a Byzantine leader. So in case of a non-faulty leader, how do we think of a non-faulty virtual leader? That's just a single, unique, non-faulty proposal being elected and everybody receiving that value. And that is the same as a non-faulty leader in hot stuff, right? We should achieve progress here. We should eventually agree on a value in this specific view. And it's important that parties can't convince each other to abandon this view by providing a proof. If we don't have a unique proposal, then we can, if we don't have a unique honest proposal, so it's either faulty or non-unique, we can send that proposal with proof to everybody, and everybody will be convinced and proceed to the next view. So a little bit of conclusion. We talked about the first three parts, the DKG protocol, the consensus protocol, and the proposal election protocol. We didn't talk at all about the gather protocol. It's another interesting protocol for consensus purposes. But if you're interested, you're more than welcome to read the archive version. It has a very nice write-up. Yeah. Oh, sorry. Thank you very much.
ask my question, I have a question. Can you crystallize the difference from that CCS20 work? What was the insights? What were the insights that enable you to improve these lines?
Can you repeat the questions for the mic, for the audience?
And if you can, let's share set up
Yeah.
the presentation.
The question was, how do we manage to improve the CCS work? So a part of it is being able to use this randomization, only running a single leader in each view instead of running many. I'm trying to remember exactly their techniques. If I'm not mistaken, that's the main technique that they use, and we manage to only have one at any given point in time. And we don't need to do kind of this round robin thing as well.
Okay, thanks.